That's fine. That's fine. So chapter 2 is pretty much acids and bases. I know the chapter on the book is also called Alkanes, Thermodynamics, and Kinetics, but this is going to be about what in your syllabus is called acids and bases. After this, we're going to be doing stereochemistry. So last week, we finished off the lecture with some diagrams. And I told you, at least if you don't buy the balls and sticks to play with at home and build the structures, plasticine and toothpicks, okay? I will be bringing these when we actually have that chapter here. I think I have 7 or 8 colors, which I can use to show you how to do them at home. So, petroleum, pretty much, it's combustion. There are 2 aspects of the reaction. It's how warm, so the temperature, thermodynamics, so how much energy is released, and how fast. How fast is the kinetics? And today's lesson should not be all revision, but pretty much most of it will be. So again, we're easing into the new concepts, and soon enough, we're just going to be doing new materials all the time. So, how fast? A barrier is for a reaction. So, how warm? It will be the energy required for exothermic. Okay? So, if something is exothermic, then this means that it will release energy. How fast? Okay? How fast is going to be how easy it is to break the bonds. How easy it is to actually start the reaction. So how fast, normally we're going to be speaking about the activation energy. So thermodynamics, it will be the energy change in the reaction. So how much energy do I need to break the bonds? How much energy do I release at the end of the reaction? Chemical kinetics, it is how easy it is to create the equilibrium. And normally, this will be controlled with how easy it is to make the product. Now, an equilibrium is always established, even in reactions that do not look like having an equilibrium. It just lies firmly to one side. In this case, it just lies firmly to the right. So, there are 2 cases, okay? You can have A to give B, for example, NO2 and 2O4, okay? Remember, you would need 2 NO2s, but it doesn't really matter here. Or you can have A plus B to give C plus D, okay? If K is large, this means you will have a highly negative delta G. Now, I don't think if you know this reaction, no, 1 second. You have not done that reaction, right? Let me change the color for the ones in the classroom. Delta G equals minus ln K. A level? No, not there. Well, analytical, this year at university. Okay. So there's a relationship between the Gibbs free energy and the constant. So the bigger the constant, the more negative delta G will be. Okay? The bigger the constant, the more negative delta G will be. And the more negative delta G will be, that means it's going to lie to one side over the other. Okay? So, as we were saying, temperature always in Kelvin. Please, at university, I never want to see the mistake of someone writing 0 degrees Celsius as temperature is 0. Okay? R 8.314. Okay? And the larger the K is, the more negative a reaction will be. And here you have a few examples. Okay? When K equals 1, when K equals 10, 100, and 0.1. Of course, just take a look at these later on, even at home. I will be having some time at home this weekend to upload all the material we've covered till here. Okay, you can just take a look and see what's happening. Now, I'm going through everything because I want to make sure that when you read the book, and I'm emphasizing, the book is important. When you read the book, you can find everything in the book, and you can understand them. Then you have the equation that you had from A level, delta G equals delta H minus T delta S. Delta H is just part of the equation. Delta H is going to be the bond-breaking, bond-making difference. And therefore, if it's going to be the bond-breaking, bond-making difference, it's going to be with respect to the energy change of the reaction. Okay? How exothermic or endothermic something is. You also have the entropy value, okay? And the entropy value is going to be dependent on whether something is going to form gas or more number of molecules, or you're going to break it into smaller pieces. That will normally create disorder, and entropy is the amount of disorder. So, a simple reaction, the activation energy will be the energy required to break that Cl to bond. So here it will be 58 kilojoules per mole. Okay? And this will have a negative enthalpy change. The enthalpy change of this reaction, you can't really get it from the data given. Okay? But here, you will, I think, get a little bit more disorder. But from the data given here, you can't really get it, okay? Because you have gas, 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 and gas. This in itself, you will get to know later on, that has a that its boiling point is very close to room temperature. Okay? So sometimes you might find it as a liquid, sometimes as a gas. In Malta, especially in summer, you can have to store that in a fridge. So some chemicals have a boiling point that is going to be around 20, 30 degrees. So if they are liquids and you store them in a bottle, they will literally explode. This has happened in the past at university. Okay? In your practicals, you'll have your chlorinated waste. Chlorinated waste in the summer, you have to store it in a cool place. Otherwise, if you have chlorinated solvents that have low boiling points, they will evaporate and they could potentially explode. Going from 2 molecules to 1 molecule, you are decreasing the disorder, so delta S will be negative. And here up to now, we're just speaking about delta G. So in the past, delta G might not have been that important for you, but now all reactions will be delta G based. Negative delta G, reaction will happen. Positive, it will not happen. We should forget about the exothermic and endothermic. They are just going to be part of the equation, just a simple part. Okay? Now, all processes have an activation energy. And this can be high or low. And we're going to have a transition state. The transition state cannot be extracted. Okay? At transition state, you can never purify and extract from a reaction mixture. And it's important to note, it's just going to be the highest energy state of the reaction. Okay? And that, from that point on, it will always, always go down. Okay? Now, adding CH4 to oxygen We all know this is a very easy reaction, but the activation energy is very high, which means that you will need to give that activation energy yourself. Another thing to note is activation energy is 40 kilocalories, whilst the exothermic energy released is minus 213. This reaction will self-react. Once it starts, it will not stop. If the energy released is higher than the activation energy, those kind of reactions will keep on going. You will have a chain reaction. Once it starts, it will not stop. Okay? Very important to note. So some reactions in organic chemistry you need to keep on heating. Others, you just heat in the beginning, and you might want to cool them to stop it from going too fast, for example. Something to note here, Volhard is an American book. Because Americans do not follow the metric system, all the examples will be in calories. In fact, for most of these energies, and for most of the books I think you use here at university, they are American published, so they will be in calories rather than kilojoules, but it will be the same thing, okay? There is a conversion. If you would want to know it, ask me later on and I'll give it to you, but normally there's no real interest how to convert them from one to the other. So, the rate of reaction is dependent on two things: the barrier height, or the activation energy, and the temperature. How fast the atoms or molecules are moving. The lower the activation energy,
Sir,
the faster the reaction will be. Yes?
you had a picture of a person who underwent spontaneous combustion. How does that happen?
Remember, these slides I take from what's present in the book. Now, spontaneous combustion, it's theoretical. I have never seen it happen to anyone in my life, and I highly doubt I will. But again, if it were to happen, remember, you need to be able to remove all the water from your body. So the energy released from combustion has to be higher than the energy required to vaporize water, which is possible, okay? If you get a goldfish, you put it in a bonfire, it will dry up and it will burn. It's possible to have that energy, but don't expect to see it at any time in your lifetime.
Okay.
Not as interesting as you might have wanted. Yes?
Someone else wanted to ask why the shoes weren't burned.
They were placed afterwards. Why the shoes weren't burned. Now,
Sir,
yes?
il-units, dak dejjem nippruvaw nikdbuhom joules per mole.
So, in organic chemistry, there is no reason why you should. Because we're not going to be speaking about mathematical calculations. Remember, for physical chemistry, check the units given. If they give you calories, use calories. If they give you joules, use joules. Normally, whatever they give you, they would want you to use that.
Thank you.
Okay. Then you've got the concentration. The higher the number of particles, the better the chance of them colliding. And if they have a better chance of colliding, they can react more. Probability, not all collisions are going to be the same. Okay? Not all collisions are equal. Some collisions will react, others will not. Here, I will introduce the SN2 mechanism. Okay? For the SN2 mechanism, the reaction must be from behind. If it doesn't happen from behind, it will not work. So the nucleophile must be on the opposite side of the bromine. So unless the approach is from the back, nothing will happen. There will be no interaction. Okay? In fact, this is why the bigger the groups are, the more SN1 is favored. And it's important to note this. Okay? The angle of approach is important. In chemistry, there are two things that will be very important that will matter. Size matters, and the angle of approach. So, rate loss. Rate measurements lead to rate loss. Okay? You can have first order, second order, third order. So in a first order reaction, you have a unimolecular reaction. One step determines the rate of the reaction. One item in that step determines the rate of the reaction. If you have two, a rate order of two, second order, you have two items colliding. Okay? And we can then measure the barriers using the Arrhenius equation. K equals AE to the power of minus EA over RT. Here, you can use either kilocalories or kilojoules. Remember, A is an exponent factor, and you will get this from books. So use kilocalories if A is in kilocalories, use kilojoules if A is in kilojoules. And this would be the potential energy diagram. You are used to this, okay? Remember, here, you have a transition state, and the transition state, you always need to write it down. So from this point onwards, you always need to write down the transition states. Jason Christopher Bonici. I'm not sure if you wanted to say something or not, because I'm only seeing 3 dots.
No, that was for something else. It's okay.
Okay. Probably not meant for the lecturer. Learn that if you want to send your messages to someone else, you have to click on their name first. Now, normally, a reaction will have a number of steps. So, let's follow here. Okay? Activation energy goes down. This is an intermediate. So any well is an intermediate. So all of these are intermediates that you can get and purify. Of course, you need to trap intermediates, and it's not always easy to do, but you could be able to do it. In this reaction, you have 1, 2, 3, 4, 5, 6 steps. And whenever you're drawing something like this, always ensure that your final product would be the lowest energy product. Okay? Your final product should always be the lowest energy product. Okay? So here's a quick problem for you. Take a couple of minutes to think about it. Which is right? On heated to 100 degrees Celsius, compound A converts directly to C. It equilibrates first with B and then goes to C. It stays where it is, or it stays where it is. Which one do you think is right? From the ones from home, you can even try to write your answer on chat. Okay? From the ones from home, you can write your answers on chat. And these will be the kind of questions you will have in your tests. So, who thinks it's A in the classroom? B? Okay. In the classroom, it is 66% who think it's A. And let me actually check something. No, I'm not gonna bother to do that. So, everyone agrees it's not C. And this is what you have to do in a multiple choice question. You can always eliminate one of the wrong answers. Then it's either it's going to convert to A, or it's going to equilibrate first with B and then goes to C. And in fact, in any reaction, this is what happens. First, you have an equilibrium for the first reaction, and then you use the product from the first reaction to go to C. Because at any temperature lower than 100, there will be an equilibrium between the two. That equilibrium might be favoring A, and here it looks like it will be favoring A, but there will be an equilibrium where you will have A forming, and from that point onwards, you will get C. Melo.
So we were just skipping a bunch.
Hmm?
Because the arrow is A is in the middle. So if you go to B, then you would skip A, you know? Oh.
I think it's A right now.
So,
So let's say so
one second.
Although that is okay.
But then
That just
One second. So, let's say, first you have an equilibrium between A and B. As soon as I reach 60 degrees, there's an equilibrium between A and B. That equilibrium could be 100 to 1 or 1:1, the ratio, but there's an equilibrium. As soon as you reach 100, A will start forming C. So at that point, because of Le Chatelier's principle, B will start diminishing, forming more A, so you can form more C. Even at that point, you would have no A, so you still need to form the A.
So the background is with A.
So this is the activation energy required to go from B to A. So there's always an equilibrium, and the reaction is an equilibrium. Remember, to go from A to B, it requires this energy, right? It can go backwards. I know that you haven't done this a lot at A level, and we're going to be speaking about this a lot in a few weeks' time. But any reaction, you can go back. If I put enough energy, I can get these stones to go back to carbon, calcium, and oxygen. Okay? So if you put enough energy in something, you can do whatever you want. Now, in this reaction, pretty much what you will have is that, let's actually remove a few things.
The answer is B.
Yes. You have activation energy here. For the reversible reaction, it will be from A to the top of the mountain. Okay? They are equal. Remember, the transition state is the same. So the energy of the transition state will remain the same.
So what was it like A was the answer?
If A was the answer, it would be a situation where you just have A going to C. There will be no B involved there.
And you say that it equilibrates first with B because the P and A is lower than A and C.
Exactly. And you have to start from B. So let me explain the question here. The question was, why does it equilibrate between A and B first instead of going directly to C? And the answer is this. The energy required to go from A to C is higher than the energy required to go from B to A. Therefore, you first form A, an equilibrium between A and B. And then from A, you can move on. Had the graph been something like this, okay? If you have enough energy to go from B to A, then you have enough energy to go to C. Okay?
And so you say first it equilibrates with A and then
States. Where do you go state to C?
Uh-huh.
A you consider as a transition state.
So the question is, if there's a reaction where you go from B to C, would A be a transition state? No, it's still an intermediate. Because an intermediate,
Can cool it and so
you can cool it and it stops. So look at the one from before. Okay? There are plenty of scenarios where, let's say A, B, C, D, E, F. Going from D to F, it's going to be very easy if you have the energy. But these fluctuate depending on reagents. So you might add a reagent that stops the reaction at intermediate E. You might add a reagent that makes the equation higher or lower. So those are things you can change. So it is still an intermediate step. In the mechanism, you will have a proper ion or compound. It might be reactive, more reactive than the starting material, but it's still a proper step. Yes?
Sì.
Anche transition state maybe way.
Yes?
Sta insomma certa temperatura dell'ozone state.
No. Because from the transition state, no matter where you go, you are going to release energy. It's going to become more stable. Okay? At transition state, you can never extract. Any questions from online?
Sì.
Yes,
Anton,
Antonio?
allora ma stax jagħmel A u mbagħad B instead of doing B before A, or no?
Yes, you could have.
Okay,
You're
just to see.
saying
Okay.
A, B, and C, right?
Eżatt.
Yes.
Okay.
Allura, tajba hija l-B.
Yes.
Okay.
So they asked me, could they have named them instead of BAC, ABC? Yes. Those are things that are done to confuse students. They've been done since my time. They will be done since I'm gone. They will be done when your kids have kids, and they have kids as well. Remember, it's never in the favor of students. If I was tortured as a student, I will torture you guys. And I will upgrade the torture because I think I'm better than who taught me. So, exactly. Negative markings. Keep it in mind. So, there are 3 types of reactions that we will be dealing with. We can break a bond to produce 2 ions. So, dissociation of a polar bond. Normally, there has to be a polar bond. It's very difficult to dissociate a non-polar bond. Okay? You can form a covalent bond, so you have a plus and a minus, and they react. Or you can break a bond whilst breaking another. This is called a concerted process, meaning they happen at the same time. Normally, we use this to actually extract a proton. We use a base to break a carbon-hydrogen bond. But this can happen in a number of different instances. For example, going back to SN2, this is what's happening. You add a nucleophile and you break the carbon-halogen bond. So, acid-base equilibrium. And from now on, whilst everything we're gonna do, you know, or you should know, this is gonna be a little bit different because of its significance. So now we're gonna speak about acidity of organic structures. And this is not gonna be about the acidity of carboxylic acids. We're going to speak about the acidity of alkanes, of alkenes, of alkynes. And their acidity is, of course, very low. But even though it's very low, having a pH of 30 or 35 will make a difference. We'll speak about it probably next week, I think. But we'll speak about it when we get to it. So an acid is something that releases NH+. So we require an acid and a base. Base, we normally use water, okay? And we use water as our solvent, as our extractant. And here we have a proton donor and a proton acceptor. This is the most basic definition of an acid and the base. Meaning that the water is giving the electrons, to a proton, okay? And you're breaking the HCl bond. From now on, H plus doesn't exist. H plus is always accompanied by water normally. So we write it as H3O plus. If we're looking at electron densities, we're going to see that lack of electrons and extra electrons, okay? Lacks electrons, extra electrons, okay? Now, with the pH scale, so pH is the minus log of H plus, and with the pH scale, we can go from HCl to NaOH, and everything in between. We should also know by now that the pH scale doesn't stop from 0 to 14. You can have negative pHs, and you can have pHs of 15, 16. Though this gets more and more difficult to obtain, okay? I think the strongest acid I've seen was pH minus 1.2 or minus 1.3. You do not want to put your hands in that bottle. With regards to bases, the strongest I've seen was pH 15. We were dissolving around a kilogram of NaOH in a liter of water. It's difficult, but you can do it. It cleans glassware really well. Both are used to clean glassware. Okay? Yes. Remember, pH equals minus log of H plus. So if the concentration of H plus is 10, that should be minus 1. That's the convention because it's the easiest way to do it. I think in one of the superhero movies, I think it was Spider-Man, they had created an acid that has a pH of minus 6 or something. It's pretty much impossible. But they were saying it could dissolve anything in the world, apart from plastic, because it was stored in plastic. But acids do not interact well with plastics. If you watch Breaking Bad, HF, episode 1,
Yeah, I
it's
was thinking
stored
about
in
that.
plastic. Okay? I saw a few more episodes, but then I got bored from Breaking Bad.
How could you?
How can you get bored with something
كيف
like that?
كيف jista' jkun se? Kif
How?
jista' jkun?
How?
Breaking Bad leġenda.
Agreed.
No, episode 1 I enjoyed. It's 2, 3, 4, and 5 that put me off.
Keep watching it, Ma. Don't give up. Hey, yeah. It's good. It's good.
Eżatt, se, don't give up, se, laqwa series
Yeah,
fid-dinja.
and then they disappoint you in the last season with Game of Thrones.
Le.
Le, ma se tqabbix Game of Thrones ma Breaking Bad, totalment
Breaking
differenti.
Bad's different. It has such a great ending.
Thank you, Fatma. Someone agrees with me. Better than what? No. No.
Now how I met your mother had a bad No, I preference so.
Well, let's continue. I might just give you a test on these and see how you do. Back in my day, back when I was your age, I watched a lot of series. So, acidity of HA. CH4 has a lower acidity than NH3, which is lower than water, which is lower than HF. Remember who's correcting your papers, Emma.
I agree with Emma, not gonna lie.
No, it's not Em, it's Emma. Remember who's correcting your papers. And this year, unlike previous years, we will have the names of those people.
I take back what I said, sir.
No. Remember, HF is not a strong acid with respect to giving up the proton. It's a very reactive substance because of the F minus. Okay, HF. Same will be here. If you increase the electron attracting inductive effect, so you add fluorines or chlorines, you increase the acidity. But these are the things you know from A11. But how will this interest you later on when we are doing alkanes and when you are doing alkenes or alkynes or halogenalkanes or ketones? They all have their acidities, okay? Normally, I would tell students to write the products, okay? Because by writing what you've got, for example, carboxylic acids and alcohols, if you write the base so you lose a proton, then we can easily find a resonance form for the carboxylate, but no resonance form for the alkoxide. And therefore, the carboxylate will be much more stable than the alkoxide, meaning the carboxylic acid is going to be a better acid. Okay, so normally we speak about HA, and the better the base, the weaker the acid. And in organic chemistry, we tend to look at the conjugate base. The better the base, the better the conjugate acid, the weaker, the better the conjugate base, the weaker the acid. Okay? The better the conjugate base, the weaker the acid. Now, these are some of the measurements that we will be speaking and describing later on. Okay? So we've got HI being the strongest acid and methane being the weakest. Please note, remember, between HI and HBr, HI will be 10 times stronger than HBr, which in turn will be 10 times stronger than HCl. The pKa values are what we'll be using in chemistry, okay, in organic chemistry. We don't really care about the pH anymore. We just speak about the pKa. So it's a little bit different than the pH itself, but this is going to be independent of the concentration, okay? So whenever we want to actually speak about acidity and alkalinity, we speak about pKa's from here on. The smaller the pKa, the better the acid. Okay. I wrote the smaller the pKa, the better the acid. Okay. I need to find the color that all of you can see, both at uni and at home. Yeah, but at home, no, it's not that neat.
By what are you time association? Why not?
He's not the first student I've had like that. عندي student البريفات تجي 1 to 1 بفتح اللابتوب. ايش بعمل؟ ما هذا قدامي. Listen. So I have to use my whiteboard on my laptop to write on it. People, if you have a chance, don't get to know people. Piece of advice. Now, here, no. Clayton, no. Acids. Caroline, we have a team. I can't see from here, okay? I mean, they're not coming up. Caroline, sorry, wrong gender. Well, pretty much what you'll have is that Ka, let's see where we can find some space to write this. Ka is equal to H plus over times A minus over HA, right? The solvent doesn't come into it. The solvent doesn't come into it. So it doesn't have to be in water. In fact, here, the table doesn't say what the solvent is. Now, normally we will speak about Ka in water, but for example, hydrogen cyanide does not really dissolve in water. Ethyne doesn't dissolve in water. Ethene doesn't dissolve in water. Oh, yes. Now, for every time we do a value like this and we use it, we'll actually speak about the solvent as well. Issa, H2O here, I'm trying to find the temperature, 25 degrees Celsius. It's not 14, in fact. Okay? And you'd expect the pKa of water, pKw is 14. We didn't expect it to be around 7. So it's different. Okay? So that must be a different solvent.
Sir,
Yes?
ammonia mhux base.
Uh-huh.
Allora kif hemmhekk acidity?
So ammonia reacted with, I believe, sodium. It will lose a proton to form NH2 minus.
Or
So at that point, it would have behaved as an acid. Yes? Mm-hmm. هناك مش pH. Because remember, pH equals 14 minus pOH, right? So if the pOH is 15, remember it's all about concentrations here. The concentration of the OH minus would be so low that the pOH would be 15. I'll have to go and look up the movie where they say that they had a pH of minus 68. I think it was Spider-Man 3, but I'm not entirely sure, so. I like those. I prefer those over Breaking Bad. Now, we'll stop with the slide. Okay? The equilibrium will always lie on the side of the weaker acid. Okay? The equilibrium will always lie on the side of the weaker acid. So you have two acids. Okay? H3O plus and HCl. The strongest acid here is going to be HCl. Okay, it's minus 8. Whereas water, H3O plus, is minus 1.7. Therefore, it will form the H3O plus. Remember, at O level, you've used this reaction. Sorry, at A level, you've used this reaction. Okay, the nitration reaction, nitrating agent. Here you have two acids, but the weakest acid is HNO3. Therefore, it will accept the proton. Okay, and we'll move on. We'll continue here for next week. Caroline, I will confirm what you've asked me with regards to the water. Why it was 15.7. I got her name right now. So I'll see you all next week. Let me pause the.
Sir.